If you want to take a break in between, just like a 1.5 hour talk.
Can or yeah. I don't know what is.
The audience is good. It's good.
Yeah. Yes, of course. Yes.
Not for the speaker, but the audience.
I'm not taking a break now, right?
Yeah.
You don't have the Japanese ones?
You're not complaining about.
And quote the director. Okay, so welcome back for the second session of the day, and it's a great pleasure and honor to have Mehrdad from University of Oxford. For those of you who don't know, I did my PhD with him, and all the things that I know about boundaries and rigidity I learned from him. So it's very nice that he decided to come here and give us a series of lectures. Thank you.
It's him and Autumn and all the organizers. Very happy to be here, to be back here. I also spent some time before I moved to US. I was here. Very happy to see friends that I hadn't seen for some time. Karan was also here when I was here. Yes. The building looks much nicer, I can tell you that. Okay. So first, I apologize. I messed up your schedule. So I have just moved to a completely new continent. So it's been very distracting. And also, I apologize in advance if I'm distracted today. Just got off the plane, got the lunch, and I'm here. And okay. So yeah, I was. Originally, I was planning to give 3 lectures introducing the boundary theory and review some applications in system algebra theory. And now I'm not sure how much you have heard about these things, so let me just start from somewhere. In fact, what I want to do, let me just start with the definition to get this out of the way. You might have seen them, and then I want to tell you what are the main use of these. I mean, how are they used in what problems? Okay. So when I say boundary in general, it means some notion of proximality, which means generally speaking, contracting measures to points in some mode of convergence in some context. So there are various ways of quantifying that, and each gives a different notion of boundary, topological, measurable, etc., etc. So let's begin with a definition of a topological boundary very quickly. So let G be, from now on, G a countable discrete group. And X always a compact and host of a space with an action of G by homeomorphisms. Now I say X is a G boundary. Sometimes I say topological G boundary to distinguish when I start to talk about measurable versions. I understand Hannah has already spoken about Poisson boundary and measurable boundaries. So this is a topological version of that. If, now as I said, now the quantifier here is you can contract every probability measure on X to every point in X by just translating that with a net of group elements. And you want this to happen, of course, in the Weikstrass topology on the space of probabilities on X. So now, if I want to give you one example to keep in mind is, so take the free group on two generators, consider the action on its boundary. I'm sure that you probably have heard about this in this series of events, but anyway, so these are, say generated by A and B. These are finite reduced words, these are infinite reduced words. With the product topology, a compact space, the action is the canonical action of just attaching a finite word to an infinite word and reduce it. Then it is a very nice example and exercise at the same time. If you want to get a feeling about these type of dynamics, this is a very good example to check that you have this property. And there are tons of examples, but maybe right away to put this, which would be almost, G is amenable if and only if every G boundary is trivial. One direction is obvious. If you take that, depends on how do you define amenability. If you define fixed point property of amenability, one direction is obvious. G is amenable. Every G space X must have an invariant probability, but an invariant probability cannot be contracted to a point unless it is itself a point. So, and well, the other direction is a little argument. But the last thing is that I want to mention before I get to applications is that there exists for every G. I mean, this chalk seems not Japanese. Every G.
Try to break it. Try to break it.
Okay. For every G, there exists a universal. Who knew breaking things would work? So there exists a universal G boundary in the following sense. Well, I will denote it like this. In the sense that for every G boundary X, there exists a continuous G equivariant function phi from here to here. Maybe I should ask you to note that from the definition it would follow the action is automatically minimal, meaning that every orbit is dense, meaning that there is no non-empty closed invariant subset besides the whole thing, which implies that any such map is automatically surjective. So this is observation of Furstenberg, and this object is referred to as the Furstenberg boundary. of G it is, well, for amenable G, as we said, it is trivial. For non-amenable, this is a non-metrizable, all the time non-metrizable, totally disconnected, very large space. The way that you can prove this is that you just take, and this is unique up to G equivariant homeomorphism. You take all boundaries, you take the product, and you take a minimal component. This is your guy. It's a very general construction. Okay. So now, before I get back to boundaries, let me just very quickly say what is the point of these type of dynamics, why they are particularly useful in certain problems in operator algebras, and actually in what problems. So upshot is they are very, very efficient in proving results of the type if you want to show certain type of positive maps, completely positive maps or states vanish on certain unitaries. And if I want to package it into one fact, this rather simple lemma is behind the main applications of boundary theory in operator algebras. And almost all the applications, one way or the other, are getting you to this setup. And the setup is this. So, and I really like this formulation of this lemma, and I always credit this to Hanfeng. This formulation, suppose that phi, I used phi, okay, let me use tau is a state on some B of H, some Hilbert space H, and U in B of H a unitary. So I want to give you a sufficient condition that this tau vanishes at U. If you can find an element A in B of H that is positive, smaller than 1, say, such that let's say tau takes value 1 at A, but U will conjugate it to something that is vanished under tau, then tau of U is 0. Okay, so the proof is just applying Cauchy-Schwarz inequality. There's nothing here, but now think about where do you get a condition like this. So an example would be the following. Say, consider, let X, example, let X be a compact G space. Let G in G, X in X be such that Gx is not X. Good. So suppose I have a representation this is not me, right? I mean, this is the chalk. Okay. So suppose you have what we say a covariant representation of this action. So suppose there are representations, let's say rho of C of x inside V of h, and you have a representation of your group into the unitary group of H, such that the G action on C of x is now in this Hilbert space is by conjugation, such that rho of GF equals to pi of G rho of F by G inverse for every F in C of x, G in G. Maybe I should say H this time. I fixed H. And for every H in G, where of course by H dot F, I mean just the canonical action of the group on the functions. So any pair of representations like this is called a covariant representation of the action. I'm going to come back to these type of actions, representations very soon. But suppose that I have something like that. And for any action you have usually a lot of these representations. Okay, suppose I have that. Then consider a state. Is that okay, or should I move up there?
Yeah.
Maybe I'll move. Now, consider a state, or let me phrase it. If tau is state on B of H such that tau restricted to the image of C of x. Now this is a state on the image of C of x, which I can think of it as a state on C of x itself. Hence I can think of it as a probability measure on x by Riesz representation. So suppose via those identification, this is just the Dirac, this is the point evaluation at x. Good. Now, then by the lemma that I showed you, tau of pi of g must be 0. Why is that? Because by the lemma, because this tau satisfies because okay, so take f in C of x such that f of x is 1 and f of gx is 0. You can do that because these are two different points. So you can always find a continuous function that separates them like that. Good. Now, but this is just applying delta x, if you like, to f. But this is the same thing as applying tau at rho of f. What is this? This is applying delta x at gf, or probably I should say g inverse f. But this is the same thing as tau applied to rho of g inverse f. Probably I should put the inverse here to look nicer. But as we said, the representation is such that tau so rho of GF must be phi of G rho of F at G inverse. So I'm satisfying the conditions of the lemma. Good. So any state on B of H that restricts to points puts me in the set of this lemma. Well, of course, in general, if you want to say something about a state, there's no guarantee that when you restrict it to the image of rho of C of x, you get the delta measure. But the power of these type of dynamics is that you have at least a way, in terms of the dynamics, to translate any probability to a Dirac measure. So if this process of translating does not disturb you, then you're fine. And I'll give you examples where this is the case. So good. I mean, probably I should, before we get too much distracted with this intro, perhaps I should also mention what kind of problems deal with are about proving, say, even let's begin with a state. A state is 0 on. Problem of the first one that these things apply to, the problem of uniqueness of the canonical trace on the reduced C-star algebra of a discrete group. So this is, I'm sure I don't need to, but let me just. So this is the span of the left regular representations, norm closure inside B of L2 of G, and these are left regular. So these are translations of L2 functions by group elements. So these are unitaries. So on this C-star algebra, you have a state, a distinguished state, which is, or if you like, I have the following state on B of L2 of G, in fact, that takes an operator x and gives you x delta E. And when you restrict it to this C-star algebra, this is a trace. And so it was a problem to determine which groups have only this. This trace always exists, always faithful. Question was, when is this the only one? So if I want to prove that this is the only one, what do I need to prove? I need to take an arbitrary trace on the reduced C-star algebra and show you that it vanishes on every other unitary. And the way you do it is precisely using that setup. I'll do it in a second. But this was the first one. I would like to also mention, and it's not only about the reduced group C-star algebra. So if you want to, I plan probably later today or tomorrow mention similar results where we could show certain unitary representations weakly contain the regular representation. Weakly containing the regular representation means that this canonical trace is continuous on that, and the C-star algebra is that representation generates. When we want to prove it, exactly we want to show that there is some state that vanishes on every non-neutral group element. So this allows you to prove a weak containment of the regular representation for a large class of unitary representations that I do mean to mention. Another, just staying on this side, on the side of traces, the character rigidity problem. Has Bashir talked about that yet?
I'm going to talk about it.
Okay, very good. So he had the first result. His proof is not, his original proof was not using these things. But I want to mention the problem, proving it is hard, but the problem of character rigidity, so it's about determining characters on a group which are in one-to-one correspondence with traces on system algebras generated by representations of the groups. And so for many groups, so the result of Bashir is that for SLN n greater than 2, SLN Z, any character, well, extremal characters are either coming from finite dimensional representations, or it's just this trace, the Dirac function at the neutral element. So if you translate it, it becomes that so character rigidity for SLN Z's would state that any trace that whose GNS is a finite factor is either finite dimensional, I don't intend finite dimensional, or it is the canonical trace, or it vanishes at any non-neutral element. I understand, but it did not make clear what these words maybe mean. But again, this comes down to proving that a certain traces or states have the property that they vanish at non-neutral elements. So as I said, Bashir's original proof is not using this particular concept, but there are later proofs of similar results who actually do use basically a version of this level to put yourself into the setup. And the whole meat is, it's the theme of this program, invariant subalgebras. So the whole meat of such proofs is to get yourself a covariant representation. And usually the hard part is that you are not, if you just give me an action, I can produce a covariant representation. But usually you are given a representation of the group, and your task is to find yourself an invariant copy of a C of X of that type, of such dynamics, a topological boundary inside, so that you can use this trick. Okay, so, and finally, I want to mention one more problem, and then I'll get to some actual proofs. The last problem that I want to mention is about determining the ideals of of C-star algebras generated, or maybe to some extent say something, let me just put it this way: ideal structure of C-star algebras generated by unireps of G. Of course, this is very general. But in particular, for instance, can you determine certain cases where these C-star algebras generate something simple with no ideals? In particular, just so again, the original emergence of this type of dynamics came with the applications into that unique trace property and determining when the C-star algebra has no ideals, the reduced C-star algebra. So now here, this is not about that particular trace, but you can formulate it, the simplicity of the reduced C-star algebra, or in general, any C-star algebra generated by any unirep of G. You can phrase it again in terms of some map has to vanish on, say, non-neutral elements, and I can do that in two different contexts. So this is simple in the sense that has no closed two-sided ideals besides 0 and the whole thing, if and only if for any G equivariant unital positive map phi from here to continuous functions. I mean, I may sound cheating, but let me cheat. So that we have phi of G is 0 for every G non-neutral. So this time I'm dealing with more general versions of states. But again, it won't be too. You can see that I can always compose such maps with some state on the target to get a state. You can do it properly, then you can put yourself into the setup of the lemma that I just erased. Or to be more closer to the lemma that I erased. So Hannah, did you mention stationary measures?
Yes.
Yes, very good. Okay. So let's make this definition, which is just generalization of what she says. So I won't. So just pick any probability on G. State tau in here is mu stationary if well, tau is not necessarily invariant, but it is invariant when you average it. And okay, maybe I write it this way. So lambda G dot lambda G inverse. So tau of dot equals to that. So tau equals to its average by mu. And then theorem is that again, this is simple. If and only if For every mu stationary tau, we have tau of t is 0 for every, okay, I shouldn't say that. If and only if there exists mu such that for every mu stationary tau we have this, for every g non-neutral. Okay. So I'm gonna give you a bunch of examples now of representations where you can apply this, and then after that I'll actually present some results about those. But yeah, I wanted to really, I did want to emphasize the point and the whole story here, so that you catch an idea when I present the results of certain C-star algebras have such and such ideal structure, or do not have traces. Where do they come from? And it should also probably makes it much more clear why these kind of representations, why those kind of representations that will appear. So examples of such representations, I mean, where do I get myself a covariant representation? Most general case is the Koopman representations associated to measures on X. So given a compact G space X, a probability measure on X. So the Koopman unirep of the action is, let's just do the pi. You can do pi nu if you like. So this is an action of G on B of L2 of X and nu. So this is translation, but the usual thing. But now the caveat is that if this measure is not invariant, so the L2 norm of the translation is not necessarily equal to L2. So this is not isometry, so you have to fix this. So you can fix this by multiplying to the Radon-Nikodym derivative square root. Now this is an isometry. And so this gives you a unitary representation of G on L2 of X and nu. This is called the Koopman representation of the action. Now,
So it's quasi-invariant.
nuke is quasi-invariant, yes. Yes, of course, thanks. G nu is in the same class as nu for every G. Yeah, thanks. Good. So this is a covariant representation. It is not really hard to see that for every f in C of X, I have, maybe I already defined it, so this is, okay, so you can embed C of X, I shouldn't say embed, but you can represent it here by multiplication operators. Every continuous function, you just multiply to L2 functions, you get L2 functions. And so let's call it rho. And then the pair rho and this pi nu gives you a covariant representation in the sense that I mentioned earlier. Now, examples of such. So, for instance, you can take the following. You can take fix x. Let H be the stabilizer. So all the G's, Gx is x, right? And now I can take the following probability measure. I mean, just take any probability measure on this. So nu be a probability measure on the set of Gx, G and G. So I mean, is my notation clear what I mean by this? So let me write something. So suppose this is like alpha y. That's, thank you. Y needs to be, okay, yeah, delta y, where y is in the orbit. Perfect, thank you so much. Exactly, this is what I meant. Good. So now this you can so this you can think of. So then you can see that if so these none of these are zero. Take them none of the so uncountable group. So it's fine. So take this to be strictly positive convex combination. Then L2 of x and nu is this. And your representation is just the quasi-regular representation of your group on the coset space. So these include all the quasi-regular representations of stabilizers of X. Good. So in particular, in the setup that we love, where this X is a topological G boundary, we can very well say a lot of things about the C-star algebras generated by these representations, where H comes from, H is a stabilizer of some point on some boundary. And by the way, there's a class of boundary actions that's very large. And the class of subgroups that stabilize them is also quite large. And you get a lot of interesting C-star algebras, abstract even in this sense. Not only that, you can also, not necessarily in this form, but you can also get your hands on quasi-regular of G mod, a subgroup of a stabilizer. So what is the break plan?
You can take a break if you want now.
Sure. Okay.
It's a good plan.
Yeah, okay, yeah, it's a good point. Okay. Let's take a break.
So we come back 2 minutes before 3:05.
Oh, that's so complicated.
You mean 3:03?
It becomes more and more complicated.
He's doing this all the time with us.
Just to wake everybody up.
Wake up exercise, I mean. 10 minus 2.
So when you write this equal there, what do you mean really? So So nu is finite, and you have a counting measure on the right side.
Yeah. So nu is just a counting measure on a not counting. It's a measure on a count of a set. Probability measure on the count of a set. So it's the same as taking that. I mean, the set is the same as G mod H.
No, yes. What I mean is that you define the representation for probability measures, and there you have counting measures. So what you mean is that there is an equivariant.
No, it's not counting. It's a complex combination.
It's just non-zero.
On the right. What
So
is
this is summation of alpha y is 1.
Now, what is Q of G over H?
Oh no, that is counting measure.
Yeah.
So but as Hilbert space they are the same.
Yeah.
I mean it's counting
I
measure is in the same
sure.
class as an so
Sure.
it's more than just Hilbert space is the same. I mean what I meant are representations are equivalent.
Yeah, okay, that's what I did.
So you send the left regular there to the
Yes.
Koopman.
G acting on this Koopman is the same as G acting
You
on
just
this.
take delta E and you get unique trace, nothing else.
So how is the weather here in Oxford?
Yeah, me too.
Better than here. Better than here.
Better than here. Is it snowing?
That's not the highest standard, right? Here it's very
I guess
cold.
it's raining there.
I think it can.
It has been.
Yeah, no, I was just wondering.
It doesn't rain as much, but it's always cloudy. So since I moved there, I don't think I've seen sun. Always cloudy. Hi, Chen. How are you? Sorry, this is Chucky. How are you?
Good, how are you?
Yeah, good to see you.
Yeah. So you're now in UK
I
already?
am in UK, yes. Just moved there a few weeks ago. Yes.
Oh,
And you are now in China?
yeah, in Harbin.
Yeah, I heard. Nice, thank you. And how are things?
Yeah, it's good.
You moved some time ago, right? You've been there for...
It's last year.
Yes. Nice.
But yeah, just heard it, yeah, you moved to the house. Congratulations.
Yeah, thank you.
Great place.
Yeah, it is, yeah.
Okay, so what you do is, because this is not amenable, there is space X on which there is like. And then what you do is you look at the probability space of that probability of X. And then you find an irreducible prime variant.
I wish this was all over. No, but actually didn't get any sleep because what you have to take.
John's like,
Yeah.
because John's, you can use the John to find
I heard the noise, I thought this was
because this is a zero, it's a chronic that you look at the extreme numbers of the closer of us. I just trained you.
靠里边的点。那就是。
It's not acceptable.
rather negative.
There should be a copy break actually.
我那基本上 pass 一半是卖上等于让他所有的那个。
我记得上次在北戴庄，在 logo 的时候，那个定义的是这么改。
这样互相觉得就是它一定是只能是来自一个。是吧？我的理解是这个意思，所以不就是这个玩意儿？他如果没有手感。
Yes, usually.
我记得别的没有。
Sorry, it is right, and so somehow
An example that we didn't
decided when teaching, I get 2 years of half
，positive environment 是怎么？那谁跟谁比的？positive environment 定义，
term is only 8
所以所有的 G 纽都小于绝对连续于纽。
因为是群嘛，一样。
对的，我觉得
weeks. Yeah, 8 weeks I teach.
G 纽绝对连续于纽，和纽绝对连续于 G inverse 纽不是一样的。
8 weeks a year.
That's just
Then I'll get the regular.
把 G 领定义到。
Emmanuel Boreal gets that. I think. No, actually, I mean, generally, they're compared to the US here, they teach quite a bit. So the regular load is, so they do our, I mean, they have formulas. It's not how they teach.
冯东一个大师，
Equivalent to the US of.
皇马他是，我不是，我是学都不算，不学。
So it is. So and they have crazy system. It's not uniformly distributed. So on every other week, I teach a lot.
This context that for them.
I mean, yeah. It's so next week is the first week that I teach a lot. Thursday 3 hours, Friday 3 hours.
You have a slab which is
他不是说3.03吗？
And that then
再过2分钟。
it's a crazy. Yeah. No, it's the first time it's crazy.
No pocket breakup.
How many minutes?
You're going to
吹手性质有点。
I will send officially the copies in the cafe.
break.
Everyone is invited. How many minutes left to 3:05?
-2.
Oh, I'm +2, right? So I start. Okay, so let me now actually prove a theorem. You see, at least the first thing that I mentioned, and then I'll just expand the proof. Yes, so let's make it a theorem that tau be a trace on reduced, then tau of g, or I should say tau of lambda g, is 0 for every g that is not the kernel, the action of g, and its Furstenberg boundary. Proof. I want to show what I meant earlier when I said if transforming your state doesn't disturb you. So this is what I really meant. So extend tau to a state on B of L2 of G. So any non-preserving extension is automatic a state because it's norm 1 and 1 and 1. Let G in G, G not in the kernel of this. Fix some point that I do not want. Okay, so fix some point Z in here and define the row of continuous functions here to B of L2 of G. In fact, first let's go at infinity of G, and then I put an infinity of G inside B of L2 of G, and my row takes F, and at element H, it's going to give me F of HZ. Then rho is an injective star homomorphism. And the fact that it is a star homomorphism is straightforward. Why is it injective? It's because the orbit of every point in here is dense. So no function can vanish at the whole orbit. So that's where I use minimality of the action. And again, this is straightforward to see that rho of HF is lambda H, rho of F, lambda H inverse. So this is what I mentioned as a covariant representation of the action of G on CFX. This covariant representation, I managed to get it inside B of L2 of G. Good. Now, very good. So now I have this extend tau to a state. I didn't give it a name. Let's just give it a name. Tau tilde. Okay. I have a copy of this inside BFL2. I restrict tau tilde to that. Let nu be in probabilities of B such that the restriction of tau tilde on rho of F is just integral f d nu for every f. Well, there is always a probability like this by Rees representation, because so this is a C star copy, rho of this is a C star copy of that. You restrict a state on the C star copy, you get a state on this, but every state, of course, is just integration with respect to a probability measure. Okay, good. Now, but the definition of a boundary allows me to find a net of group elements who will translate this to the point I want. So obviously the point that I want to converge to is the point that this guy moves. So since G is not in the kernel of the action, there exists some x naught such that gx naught is not x naught. Choose. Now, from this point on, I already well, by definition, there must exist a net GI such that GI new converges to this. Good. Okay, so now, and so one observation we want to make, so when I translate this nu by a group element and I integrate a function, it is the same as if I translate the function and integrate with respect to nu. I mean, you do G and G inverse, right? So applying these, integrating with respect to these of a function is the same as integrating translate of the function with respect to that. So all in all, what I want to say, and translate of a function, as we already know, as I mentioned, is this. So if you like, note that GI new, or perhaps I should write like this, f dgi new, this is the same thing as applying tau tilde to lambda g or g inverse or gi. Rho of f lambda gi inverse. I mean, here now, maybe inverse is here. Just allow me, I mean, I had a flight this morning, so I cannot now say if it is here or there. I mean, either it's inverse on this side or that side, it doesn't matter. But yeah,
It's okay.
it's okay, good, thank you. Good, so keep that in mind. So now, all right. So I'm getting a with composing with this conjugation. I'm now thinking of a net of states that are applied to rho of f. But now I have a net of states on B of H. But the state space of any unit of C-star algebra with Wig-star topology is compact. So take a subnet, or I don't want to now do double indexing. By passing to a subnet, we may assume that they Wig-star converge in the sense that there exists state, let's call it psi eta and B of H, such that tau tilde of lambda gi rho f, I mean, I don't even, so let's just do t. I'm doing it, I'm taking the limit in state space of B of H. This equals to tau of t for every t in B of H. Not equal, so converges over I. So composing this state by this conjugation gives me a state on B of H, so I get a net of states on B of H. I take a Wig-star limit, Wig-star limit point. As to the subnet, I assume these converge already Wig-star. So you have you may choose, not assume. You may choose a state. You don't need to assume. You may choose a state such that this happens. Okay. Now, this process did not disturb me because all I cared about from the beginning, I mean, all I care about is this tau applied to that. So now, it follows now when I apply it to rho of f, so it is the limit, weak star limit of these, but composition of tau tilde with those were just integration with respect to gi nu, but these were weak star converging. This was the choice of gi to delta x. So this is the same as evaluation, point evaluation at x naught. So this is f at x naught. For every f in C of the boundary. On the other hand, what is eta on lambda g? Okay. On the other hand, eta applied to lambda g is the limit over I of tau tilde of lambda gi, lambda gi inverse. But these guys are all in this reduced star algebra. And this was an extension of tau. Agreed? So this is the limit of tau of these guys. But tau is a trace. So this whole process did not change tau at all. But now, what happened was, I just extended tau to any state. I took any state extension, just restricted to the other side. And then using the dynamics of other side, I transformed the extension, but I transformed it in a way that it did not change. They all remained extensions of the same trace. But now, what do I have? Now I have a state on B of L2 of G who restricts to delta x naught on the image. So now I can apply the lemma. By the lemma, it follows that so tau of lambda g, which is eta of lambda g, must be 0. So then this shows you that if the action has no kernel, then you have no trace besides the now, the exact same proof can be applied to any covariant representation of the action of G on continuous functions of the Furstenberg boundary. Any covariant representation. There was no point that I used L2 of G being my Hilbert space. The only thing that I used was the copy of the continuous function of the Furstenberg boundary and the copy of the group interacted in the way I wanted. Exact same proof, you don't need to change anything. Just change lambda G to pi G. And so now I gave you the examples of such covariant representations, now you can tell. But what does this tell us? And one last thing, also there is nothing special about the Furstenberg boundary here. Again, at no point I used the fact that this was the universal boundary. Except that it is the most efficient one if I want to do these things, because the kernel of, if you extend, the kernel becomes smaller. So you rather to work with an extension to have a smaller kernel. But the general result that I'm not going to write, but I mean, it's good to notice, is that the exact same proof shows if you give me any G boundary X, any covariant representation of the action of G on X, then if you have a trace on the C-star algebra generated by the group, that trace must vanish outside the kernel of that action. No need to change it. Jacopo has been talking about SL3 over SL2. So SL2 appears as, so SL2 stabilizes points in a boundary of SL3Z. So we showed with Bashir that the quasi-regular representation weakly contains the regular representation. So we show that this canonical trace is continuous there. And basically the argument is this. And you have, well, loads and loads of more examples. Yeah, I would like to mention, for instance, for C-star algebras who are here, even very abstract C-star algebras like the Kunz algebra is a C-star algebra generated by the quasi-regular of a group over a subgroup that is a stabilizer of a boundary. So this is by no means this is a restricted set of examples. It's actually very general. Okay, but good, but still you see that we feel it feels very lucky and it feels very special because, yeah, I mean this trace property allowed me to do my work without even moving this. So you see that the reach of this is that you can only prove if a trace exists, then such and such. But it doesn't tell you if the trace exists or it doesn't exist, etc. So now, but for other problems, like the problem of C-star simplicity, which I mentioned, that you probably have to do something like that with the stationary states, then this does not work. Because if this was not a trace, when you moved the extension, you would have moved the original state as well. So you may end up proving some other thing is something. But still, actually I do want to do the proof of yeah, I I would like to show you when you can then. So in those cases, it should not be surprising to you that in those cases, perhaps I want a boundary that is a little bit more special. So it's a little bit extra boundary. So let me do the following example, very concrete. Let's do F2. Consider F2 acting on its boundary. Let us take, and F2 is, as I mentioned, generated by A and B. So let's take the uniform measure. Then there exists, there's absolutely nothing special about this, except that it's just the simplest one to mention. A unique mu stationary probability mu on the boundary. Hannah may have mentioned this example or this particular, in particular, this is an example of the Poisson boundary. So this, with that measure, is the Poisson boundary of the random walk of the symmetric random walk on the Cayley graph, which is just a regular 4-tree. If you just walk uniformly in 4 directions with probability 1/4, the space of all final destinations, you can parameterize it by this boundary, and the probability of taking a particular path is governed by this unique mu stationary probability. Okay, so this is a fact. This is a fact that there is a unique stationary probability measure. Now, this makes this fact makes. I told you at the beginning, this action is the example of a boundary action that I would like you to keep in mind. But this fact makes it an even more special type of boundary. It gives it a bit of a stronger property, and I want to show you how I can exploit that. Okay, so let me use this fact to prove to you that any stationary state on the mu stationary, for this particular mu, any mu stationary state on the reduced group C star algebra of the free group has to vanish on every non-neutral element. Hence, by the theorem I mentioned, it must be simple. And I will give you the proof why this implies simplicity. It's a very simple observation. Let's not distract for now, so let me do this proof. Okay, so now let me take tau be a mu stationary state, as I defined earlier, on this. I want to run a similar trick. I want to extend it, restrict it to the other side, and play the game. Let tau tilde be an extension be a at this point be a mu stationary state on E over 2 of G extending tau. I realize that I need to justify. So I'm going to justify it here. Okay. So this is a very general fact. Observe.
You're going to justify that there exists such a state, right?
Yes.
Okay. Yeah. Okay. No. I mean, it's not completely obvious because you have to extend it.
Because, yeah, I mean, this also tells, allows me to tell you why proving unique stationary state gives me simplicity. In fact, it's just the same thing. So maybe it's efficient I do it now. So in general, very general, let A be a unital C-star algebra equipped with an action of G by star automorphisms. Good. Let mu be a probability measure on G. The map that takes a state omega, a state on A, and gives you what we say mu convolution. The following state, another state, which you get by averaging mu of G omega of G dot. So G acts on the C-star algebra. So each G is an automorphism of the C-star algebra, hence it gives you a map from the state space to the state space. You compose with the automorphism. You compose the state with any automorphism, you get another state. So this is the composition of the state with the automorphism defined by G. And then I average them. This map is continuous convex on state space. So now state space is a compact convex space, and now you have this this unique map. Then there is a general fixed point theorem that tells you that this has a fixed point. It's Kakutani's fixed point theorem, I think. So
Markov. For the Russian.
Okay. I apologize to. Yes, Markov-Kakutani fixed point theorem. So I mean, it's not hard to do. You just so in general, if you have such a map on a compact convex space, now you can take the C0 averages. So you compose it with itself n times, and then you take the sums you take the combination of these and take a limit point, and you see the limit point must be a fixed point. T absorbs any limit point of its C0 averages. So you always, hence has a fixed point. And I want to emphasize that this is not hard to prove, that any such map has a fixed point. Okay, and any fixed point is like our definition of a stationary state. So what did we show? What this tells you is that you give me any unit of C-star algebra, any action of G, any probability measure on G, there's always a stationary state. And that is the advantage you get compared to invariant ones. Invariant ones may or may not exist. But these ones always exist. Good. So this is the advantage. Disadvantage is they are not invariant. But now before I go back to the proof, I mentioned theorem that this is simple. I said if and only if one direction is not easy, but why don't I just say it this way? Let A be a unital C-star algebra equipped with a G action. If there exists mu such that every mu stationary state on A is faithful, meaning that it does not vanish on any positive element on A, then A is simple. Well, I should say G simple. Then A has no G invariant closed ideals. Why is that? Just a simple observation. Suppose that you have a G invariant ideal. Go to the quotient. Because the ideal is G invariant, the action can be now pushed to an action of G on A mod the ideal I. Now A mod I is a G C-star algebra, a new C-star algebra with a G action. But then this tells you that now you have a mu stationary state on that. So now you have a mu stationary state on A mod I. You put it back. You're going to get a mu stationary state on A, because the map that sends that goes from A to A mod I, the way that you define actions, this is compatible with actions, so nothing changes. So now you get yourself a stationary state on A, but this guy now vanishes on I. You're not allowed to. So here, this general fact only tells me that I don't have ideas that are invariant under the G action, but in our setup, what is the G action? G action is by conjugation unitaries inside the C-star algebra. Any ideal is invariant under our action, if the action comes from within. So this you can just get rid of in our case. So this is how, so if I have a mu stationary state such that, if I have a mu such that the only mu stationary state is that trace, the canonical one, I know the canonical one is faithful. So then my C-star algebra is simple. And that's the fact behind this. Okay, so now I can get to the end of this. Well, almost. So extending tau. So now you know that by the same fact, if you take all the extensions of tau, all the states who extend tau, that will be a convex compact space, and mu is going to operate on that to give you such a map. And again, you can apply Markov-Kakutani for the same reason. I mean, this statement can be improved that any stationary state can be extended to a stationary state. Okay, let me leave it to you to make that observation. Okay, so I can do that. I call it tau tilde. Then, similarly to before define rho from C of the boundary of F2 to B of L2 of G of F2. Again, you fix a point and you define the map exactly as I defined last time for the Fulton-Beck boundary. Not this is more concrete boundary. And it satisfies the same properties. I mean, it's just the same similar map. Then you restrict yourself to this copy. Now this row that we defined is compatible with the action. And that allows you to observe that when I restrict this to this copy, the probability measure that I get out of this restriction is mu stationary. But I know that there is only one. Rho of any f is integral of f d nu for every f continuous function on the boundary. All right. Now, I think you mentioned that along every path this measure converges to yes. Yes. So I'm going to write a fact similar to what Hannah told you about actual boundaries. This is also for stationary probability measures on measurable G spaces. That is also true in the C-star algebra case. Exact same proof again. I mean, you don't need to change anything. It's just a direct consequence of Martingel's convergence theorem. Not much. So the theorem is this. Exactly as in the classical case that Hannah mentioned to you. Let A be a unital, let me say GC star algebra. So it's a C star algebra equipped with a G action by star automorphisms. Mu a probability measure in G, and nu a mu stationary state on A. Then here I'm going to assume everybody were present in bed level. Is that a good assumption?
Maybe.
I take it as yes. Then
Also, we are like 5 minutes above the stopping time.
No, but he started late.
you're not giving us coffee, so there's no.
No, you took the 5-minute break.
Okay, so then maybe I'll just write this sentence and I'll continue tomorrow. Then for almost every path, let me call the path omega in the G mu random walk, the sequence of Gn nu converges V star to a state, let's call it tau sub omega on A. So in and I'm sorry, and the original tau can be recovered from these guys when you integrate along the path space. So this is so the classical one that she mentioned. So this is actually the point of stationary dynamical systems. This theorem is the point. This is due to Furstenberg. So he observed that when I'm working with non-invariant measures, it is correct that you don't know what happens when you translate. But if your measure is stationary, you do know when you translate where do you end up. Not only that, but you can recover your original probability measure from the limit points by integrating them. So what we are going to do in those cases where my boundary actually matches with the boundaries that Hannah mentioned with the measurable version of these boundaries, then I can apply some random walk theory techniques. Then it is true that when I move the extension, I also move my original tau, but this time I do it in a smarter way. I move it along the path in the random walk. And a stationary probability space, as Hannah defined, is called a mu boundary in general, if these limits are delta measures. So in that case, as it was mentioned, with this measure is a mu boundary in the classical sense, which means that those measures, when I restrict them to continuous functions on this, are delta measures. Hence, I am precisely in the setup that I want. I can say what I want about these guys, but then I integrate them, and I can say what I want about this. I'll finish the argument tomorrow.
Do you have any questions from my back?
Should that tau be new?
Which one?
I mean, what is tau?
Oh, it is new. Am I? Yeah. Thank you so much. Yes.
So if there are no more questions, let's thank Mehrdad again. So we meet tomorrow at 9:15.